Hello everyone, this is Amritpal Singh. Welcome to the next video. Guys, in this video, I'll be talking about decision trees. In my previous video, I've already talked about the naive-Bayes algorithm, right? How it works. Today, in this video, I'll be giving you a brief introduction to what decision trees and how they work, right? Let's get started. So actually, we are having a term available. It's called CARD. It's an umbrella term which consists of classification and regression trees. But in this, because we are dealing with classification, right? So we'll be talking about classification only, right? So decision tree, if I talk about theoretical way, it's a supervised learning algorithm that works for both categorical and continuous input and output variables. But for this video, will be more focusing on the categorical data, not the continuous data. So we can predict both categorical variables, which is a classification tree, and continuous variable, which is called regression tree. So we are more focusing on the classification tree in this video. So this is how the decision tree look like it's a diametrical structure. We are having root node available. In between we have internal nodes. At last we are having a leaf node. So your tree will end up, we can say tree is complete when you got the leaf node. So decision tree is a flow chart like structure with the if else condition. The top node is called as a root node, which I already shown you in the diametrical notation. Followed by we start the question from the root node, then we move through the tree branches according to which groups you belong to until you reach a leaf node. As I've already stated that your tree will be complete once you reach the leaf node. It means our classification is complete at that moment. So now before we jump into the example that how the decision tree works, we have to talk about impurity, because it's an important topic in the decision tree subject. So in this case, you can see we are having three squares available, right? We are having squares with all blue balls. Here we are having some greens are there. Here we are having equal number of greens, equal number of blues. So what's the meaning of impurity here? So impurity meaning is that in this case we can say the square one is completely pure. Square 2 has little impurity. This is having a more impurity. So what it means? So in this case, actually in the decision tree actually work for homogeneous type of data. So decision tree always give you the data which is homogeneous. This is a homogeneous, it's having little problem, we can say it's little impure. This is more impure, means because we are having equal number of greens, equal number of blue, right? So how we can measure the impurity in the data? So we can do it with the help of entropy and Gini index or Gini impurity. So what it means? So entropy is amount of information needed to accurately describe data. So what it means? So if a data is homogeneous, it means, as I already told you, the ultimate objective of the decision tree is to end up getting us giving us the homogeneous data. So if a data is homogeneous, means of similar type, then elements are similar, it means entropy will be 0, which is pure. This is which is we are looking for. Else if the elements are equally divided, then we can say entropy move towards 1, which is impure. Like in the previous example which I already told you, this is completely pure, this is having little impurity, this is it's having more impurity, right? Moving further, so what is Gini index? Gini index measure the impurity in the node. It has a value between 0 and 1. So Gini index of a value 0 means the sample is perfectly homogeneous, like the first example in which all were blue and all elements are similar, whereas Gini index of value 1 means maximum inequality among the elements, like in the case of third case which I shown you in the diagram. So this is the formulas, mathematical formulas, that how it works, entropy and Gini index. But our objective this video is not to go inside the mathematical way. I just want to show you like in a easy language that how the tree works. So let's take example. So let's suppose we are having two variables available, x1, x2, and in this case we are having some data points available, which is green and red. Okay, so with this example I'll be showing you how this tree work. First of all, we are having a split available. Actually, we have to keep on splitting a data till the time we get a homogeneous data. This is the point, right? First of all, we have a split available at x2 equal to 60. It means below 60 we are having this data available, above 60 we are having this data available. So it's a split one. Then we have a split 2 available at x1 equal to 50. In this case, you can see now with this split, what happened is the green has been separated, red has been separated. It means, but the below 60 still we are having a impurity available. It means still not homogeneous because red and green are mixed, right? So moving further, then we have a split 3 available at x1 equal to 70. With this split, what happened is we are able to achieve one homogeneous data, which is red elements, but still this data, this region above 70, it still require another split so that we can divide the green and red, right? Moving further, the last split here is happening approximately at 20, x2 equals 20, where we are having now green are separated now and red are separated. So you can see now this is the end of the tree, because we're able to divide data in such a way that we are having a homogeneous data, right? So let's see how the tree works, how we can make up a tree with this splits. So when we have a split 1 available at this x2 equal to 60, this is how we have to start. X2 less than 60, we are having two ways available, we have two possibilities are available, yes and no. Okay, this is a split 1. With split 1 we are able to construct this portion of the tree. Moving further, if we have a split 2 available at x1 equal to this x1 equal to 50, you can see at no. Okay, at no, then we are having this split available. In this case, what happen is, with this split we are able to divide the green and this red properly. That's the reason we are able to reach to leaf node. You can see red and green, it means is the end of this branch. It means to right side we can say we are able to now complete this branch, because we are end up getting the green and red, right? I'm again repeating. With the first split, what happen is, we are having at x2 equal to 60, we are having two possibilities, yes and no. After second split, what happen is, with this no means less than this less than 50 means less than 50 we are having green, and more than 50 we are having the red. Okay, it means we are able to achieve the leaf node with this, right, with the split 2 on the right side. Moving further, with the split 3, it means where we are having x1 equal to 70. Again, this it's 70th position. You can see again we are having two cases available, yes and no. With the left side, yes, of course we are able to achieve the red one, but why we don't have a green here? Because to right side still we are not sure, because it's a mix of green and red. On the left side, less than 70, it's completely red. That's why we are able to write this, draw this rectangle with the red. It means we have achieved the homogeneity in this case, but the right side still it is left. It means we are still looking for the last split, which is split 4. But with the split 4 now, you can see less than 20, because we have a 20th range available. Less than 20, we are having the red ones, and more than 20, we are having a green ones. So it means now this tree is complete with the split 4. I hope you must have understood from this short little video how the decision tree works. My objective is to make you understand with the easiest language, although I haven't went to the mathematical notations or mathematical formulas that how this entropy or Gini index got calculated. It's a separate subject. So in the next video, I'll be showing you how we can implement the same this tree thing in the RStudio. Thanks for watching, guys. See you in the next video.